Now we will come to the topic of forced vibrations. A forced vibration is defined as a form of vibration which is kept ongoing by an external harmonic force, by an external excitation, which is kept ongoing by an external excitation. So as long as the external excitation will be present, the vibrations will sustain. The vibrations will not die down in time. The amplitude will remain constant. So even if the system is having the damping, or even if it is not having damping, the forced vibration will continue as long as excitation is present. The excitation can be of different form. It can be sinusoidal or a periodic function. So, but for understanding the basics, we'll consider sinusoidal forcing first, and then that will give us insight that how a system behaves when it is subjected to external excitation or forced vibration. That theory can be later on, it can be developed in much more detail for any general excitation, any general forcing function, because by Fourier series, any periodic function can be decomposed in the components of sine and cosine waves. So any periodic excitation can be for that. So we will consider in the present case harmonic forced vibration. That is a forcing function is a sinusoidal one with damping. With damping first we consider, and then later on we will extend the results of damping by undamped case. So later no damping. That will be considered towards the end of the section. So in that case we simply set up C is equal to 0. So why are these oscillations important? These are important because in industry, by by rotary unbalance of rotating component, you see periodic forcing of the structure, periodic forcing or periodic load on the structure, and this structure starts to resonate or vibrate. If it is not in the resonant condition, it will start vibrating. So as long as the machinery is moving, the component is moving, let's say car or industrial press or any industrial machinery, as long as it is moving from engine, that for that much period of time there will be the excitation, and excitation will lead to vibration. So it is important to understand the amplitude and frequency of a vibrating vibrating mechanical system. That means it is having some stiffness K, it is having some inertia M, that is what is needed for setting up the uh, oscillations. So with external forcing, so it's such a system which can naturally vibrate at a natural frequency. If such a system is made to vibrate by an external excitation, then how the amplitude and frequency will look like, that is the interest of present section. Because amplitude and frequency, they will depend on external excitation. For different external, let's say some force F is periodically applied with with angular frequency of omega t. So this is external excitation in the formula form. So the nature of F, what is the magnitude of F, what is the frequency of externally applied. The sigma system will have its own natural frequency natural omega n determined by square root of k by m. Then you are forcing at a function omega, forcing at a frequency omega. So F sine omega t applied. So then it is not able to resonate at omega n also. It is not able to resonate at omega also, and there will be some other frequency where the system will resonate. So that will be the frequency of force oscillation. So frequency and amplitude of forced vibrations are different from the plane vibrating system or the amplitude due to the force oscillation. So we have to find the main quest is to find relations between between this natural vibrating system and force system, natural system and force system. The combination of them, how it will appear. Then third aspect, we have a damping also in the system. So that will also lead to some deviation from the natural behavior. So we will again define our vibrating system with the help of spring mass system. The same will apply for any mechanically vibrating system. The spring will have a stiffness of K, the mass is M, and then we have a dashpot attached for damping that is having a damping constant of C. And now in this system, an external force is applied that is equal to F sine omega t. So that is applied here. So if you draw the free body diagram of mass m, there is a position below the static equilibrium line, and there is a displacement x below the static equilibrium. X is positive downward, x dash is positive downwards, x double dash is positive downward. So the damping force F damping will be equal to P x dash, that will be towards the top, that is opposite to the velocity, and the spring force, that will be equal to Fx, that will be equal to Kx, will also be towards the top because it is opposite to displacement, and the inertial force Fi, that is equal to mass into acceleration mx double dash, that will be also towards the top, so the opposite of the acceleration. And then now you have the resultant of, now you are applying a sinusoidal force in the positive direction. So you have positive direction downwards. So F sine omega t is applied downwards. So sum of positive forces is equal to sum of negative forces. So you will get F spring plus F inertia plus F damping is equal to applied force, that is F sine omega t. That is the forcing. This is the forcing or the excitation which you are talking about in the forced harmonic oscillation. Forcing or excitation. So F of spring is kx. So we will write down the initial force first, acceleration in descending order, then damping, that is Cx dash plus the spring force, that is kx, is equal to F sine omega t. So this is the equation of forced damped vibration. Now, before going further to solve the equation, get a solution of the equation, we will lay down some basic observation. The first observation is that omega is different from omega n. So the forcing frequency is unknown. It is different from omega n. Omega n is the natural frequency. So you should, because till now in our convention we have used omega for the natural frequency, you should not get confused with that. Omega n is the natural frequency, we'll use from now on. That will determine the stiffness of the spring divided by mass of the object or mass of the system, that is square root of k by m. And so omega is not equal to omega n, and omega is a constant property of excitation. So it is a known quantity. It is not an unknown quantity. We are not solving for omega. We are just solving for displacement. So we have a forcing on our system. We should know at what frequency the forcing is applied for getting the solution. So omega is a known quantity. And what about F? F is the amplitude of excitation force. So how much maximum, if you just consider the plain spring system, so you have a massless spring, then this forcing excitation force can cause some displacement in the massless spring. So how much that displacement will be equal to? Let's say this displacement is named as xs. So this is a displacement due to excitation force, just the pure excitation force in case the system is massless and dampingless and no damping. So you just consider a spring system, that is only the flexibility is there in the system, and in that case if F is applied, what will be the deflection? So the deflection excess will be equal to F divided by K. So this is the displacement due to excitation force alone, and there is no mass in the system. So this is what is the pure effect of excitation on the system displacement, on the displacement of the system in case no mass is there and no damping is there. So because of mass and damping, there will be some natural frequency coming up, and due to damping, there will be a lag behind the force and the displacement that we will see when we derive the solution from the equation of force damped vibration. Since F is the maximum force, amplitude of force, so the excess is the maximum deflection, the forcing alone. No mass, no damping. Now the solution of the equation of forced damped vibration, that is here, is having basically two parts. Because this is an inhomogeneous equation, till now we have considered all homogeneous equations. Homogeneous equations are those where you have x double dash like ax double dash plus bx plus cx. All these things, right hand side is 0 in the homogeneous case. Homogeneous. So there is no constant or forcing function in the right hand side. Everything is 0. Summation of all the derivatives of x is 0. And this is homogeneous case, but now we have an inhomogeneous equation, that is mx double dash plus px dash plus kx equal to f sine omega t. So for the inhomogeneous equation, we know from our mathematics class that the solution consists of two parts. One part is called complementary function, and other part is called particular integral. So it is known that the complementary function is nothing but basically the solution of the homogeneous equation. So if you set RHS is equal to 0, then you will get the complementary function. So in this case, complementary function will be the solution of equation mx double dash plus cx dash plus kx is equal to 0. So complementary function, and this we have seen that it is nothing but the case of damped free vibration. So we are not interested in the complementary function simply of the reason because it's a damped free vibration. So a damped free vibration, whatever the damping ratio is there, it will eventually die out in time and it will become 0. So it eventually becomes 0. So we don't need to bother about this case. We are only interested in the particular integral. So particular integral is the solution of this equation itself, mx plus cx sine omega t. So it can be easily demonstrated that the particular integral will be the real solution of the forced vibration case, and there the amplitude is not dying with time, and the amplitude x will be something different from the case of the free vibration. In the free vibration, you got from A and B, by determining A and B from initial condition, you can get the amplitude. But here the x will be something different from the case of free vibration. The x will also be different from the case, something from the case of the simple the plane forcing case. So in that case there is no mass and no damping. In that case you have a deflection also. So it is this x is different from static deflection amplitude due to the forces alone, amplitude due to force. It is also different from free vibration amplitude. So free vibration amplitude, if you see the case just when there is no initial velocity, is basically equal to initial displacement x0. So free vibration equation is x equal to x0 cos omega t basically. So initial displacement only matters. So it is different from either xt, xs or x0 in the case of free vibration. However, it is a combination of these two because both of the components are working here, and it will also depend on the damping. Because due to damping the displacement will lag behind the force, and this lagging is controlled by how much damping you are providing. After you provide the force, it will take some time for the displacement to happen in a damped system. So it will depend on damping, stiffness, mass, everything. And we are not worrying about the complementary function, that is initial transient. So hence in a force vibration system, after initial transients some oscillations will be trying to adjust themselves. Fluctuation will be there. The steady state will be like this, what is drawn here. The steady state oscillations will be of the amplitude of x that we don't know, we have to determine. It will depend on various functions against time, and it will have a angular frequency of omega. So the omega frequency is coming because of the property of the particular integral. The particular integral, if you see my textbook, it is directly derived by integrating this equation. So if you integrate this equation, finally you want to get the function x, and as some integration of the left hand side, and you have to use some mathematical identities, integration methods, different integration methods to achieve the solution. But you will see that when you are integrating the function on the left hand side, there is sine omega t. You will either get cos omega t. Even if you differentiate, you will get sine omega t, or so sine or cosine functions only. Integration will give sine and cosine functions only, or maybe tan or cosec, these kind of functions only, 1 by sine, 1 by cosine, and sine by cosine, these kind of functions only, trigonometric functions only, with the angular frequency omega. So hence the solution will have an angular frequency of omega only. So omega, as you remember, was the angular frequency of excitation. That is a known quantity that we are imposing on the system of excitation. So hence, since we know that the steady state solution will be of some amplitude x that we have to determine, and it will have an angular frequency of omega, so we can safely assume as the final solution of this equation xt, and we know that the solution will be a sinusoid because the particular integral will be giving us cosine and sine functions only. So after doing all maths, we are going to get some equation looking like this, having an amplitude of x and a sine omega t, having a time angular frequency of omega t, and plus phase phi. So like this phase phi can be simply understood like this, like if you have cos omega t plus sine omega t plus something else, and some trigonometrical quantities, when you sum all these things and you simplify, you get a quantity in the addition here. So you will have, like say, half 1 by root 2 cos omega t, and root 3 by 2 sine omega t, and this will be equal to cos 60 sine 45. And when you sum all these things, you can relate all the complex combination of cos and sine into a single sine function having the same variable, that is omega t here, plus a phi phase difference. So this is a solution that we can assume which will be solution of force vibration. Now we are doing here the analysis in a reverse way. We are assuming the solution. We don't know x yet. We know omega, that is a given quantity, but we don't know phi yet. What is the phase difference between the actual displacement and the forcing? So forcing, you know, is f sine omega t, and displacement is sine omega t plus phi. So displacement is at phase shift of phi from the forcing. So that is not known, that we need to calculate. That will depend on the property of the system. So phi is the phase angle and the x is the amplitude of oscillations. So these are the two quantities that we need to determine. If that is determined, the solution is complete. Amplitude of oscillation in the steady state. After the initial transients have died down, the complementary function has died down. So we have to determine x and y for the completion of solution. Now for determining these quantities, we'll use the method that I demonstrated while we were covering the harmonic oscillations. So this is also a harmonic oscillation, the force damped force oscillation case. It's also kind of harmonic oscillation only. All these things, free and damped and force are harmonic oscillation only. So we can use the method of vector diagram. It becomes quite simple to visualize the problem and find the solution without going too much into the mathematical derivation. So I'll just put a brief recap of what we saw in the vector diagram. We saw that a harmonic oscillation can be represented by a vector rotating at an angular speed of omega, and the position of this vector on the y-axis or on the x-axis gives the harmonic oscillation, because that is the position is equal to cos omega t or sin omega t. That is a harmonic oscillation. So the this any and if this is a displacement vector x, then the velocity vector. So if x is equal to, let's say, position on the x-axis, we want to consider here. So theta. So theta is equal to omega t. Theta is equal to omega t, because this vector is moving with omega, and that angle from axis is equal to angular velocity into time. So then x, the equation of for x is some x0, that is the amplitude of oscillation length of the vector, cos omega t, then x dash is equal to minus x0 sine omega t. So this this is at 90-degree phase shift, because sine cos 90 plus omega t is equal to minus sine omega t. So this thing is pi by 2 shift. So this is a velocity vector v. It will have an amplitude of, and this is x0 omega. So amplitude will be x0 omega, and the phase will be 90-degree from the displacement vector. And then acceleration x double dash will be minus x0 omega square cos omega t again. So this cos omega t, so cos pi by pi plus omega t is equal to cos omega t. So this is 180-degree from the displacement. So this is acceleration. So and the magnitude of acceleration vector is omega square x. So like that we can determine we can represent a harmonic oscillation on vector diagram. Now in the present case we have this equation that needs to be solved. Cx plus kx equal to f sine omega t. So everything we assume, and we have assumed the solution of form x equal to x xt as a function of t, as a function of x sine omega t plus phi. So if you represent on the vector diagram, let's say you know this displacement xt in the vector diagram. So in the vector diagram, if you plot this vector xt, it will be a vector of amplitude x and at a and phase angle phi from the zero position. So this is our displacement vector. Now, what about the spring force? Spring force vector is kx, so it is nothing but exactly k times x. So this is spring force kx. And now what about cx dash? So as you saw that the x dash vector is x dash is velocity, that is 90-degree shift from the x. So cx dash will be at 90-degree shift, and the magnitude we can get from this equation, the x dash will be equal to x omega cos omega t plus phi. So the magnitude will be x omega. So this is cx dash. So the magnitude will be equal to c capital X omega. And then we have the mx double dash vector. Mx double dash, you saw that it is 90-degree opposite. It is 180-degree opposite. Acceleration is 180-degree opposite to the displacement. So mx double dash will be looking like this. And for that we have to determine x double dash, that will be equal to minus x omega square cos sine omega t plus phi. So this will be since we have taken negative direction, so minus is already taken here. The magnitude of this will be x omega square, and here x double dash will be x omega square, and then m is will be multiplied. So mx omega square. So you see that all in these cases we are talking about amplitude. Kx is the amplitude of this force, cxw, and all of these are rotating in vector space with equation of sine omega t plus psi. This is initial. Now you see that summation of all these three vectors, kx, cxw, ms square, all these three vectors, force vectors, must be equal to the right hand side. Left hand side should be equal to right hand side. So if you take resultant, if you draw a resultant of these three forces, it will look like this. So this resultant should be equal to the right hand side, and right hand side is f sine omega t. And since sine omega t is common for all this diagram, so this will be equal to f. That is the amplitude of forcing function. That is the maximum forcing applied by the excitation. So we form this vector diagram. Now we want to still we have assumed the solution in the form of x and xi. We don't know x and xi. We will try to get it from this diagram. So from this diagram you will see that the summation of these three vectors are equal to f mx square. So if you drop a right angle perpendicular from here, form a right angle triangle here, then you will see that the sum of the base and the perpendicular square will be equal to hypotenuse. So hypotenuse is f, so f square from the right angle triangle here, let's say O P X S, let's say, so from triangle OPS, just drawing it so that you are able to visualize. OPS hypotenuse square is equal to base square. So base is kx is this length from O to, let's say, L. OL is equal to kx, and x is the amplitude of oscillation, and OP we have to find out, and we know that PL is equal to, this is a square, this is a rectangle, so PL is equal to mx omega square, x omega square. So OP will be equal to kx minus mx omega square. Remember here everywhere we are talking about capital X, that is the amplitude of the oscillation. The small x is actually what we want to determine as a function of time, but capital X is the amplitude with which all these diagrams are drawn. The vector diagram is in terms of amplitude and phase only, and the projection of that on axis can give you the real displacement. So if you just draw here that OS square is equal to OP square plus PS square. So OS is force F square equal to OP we saw is kx minus mx omega square and whole square, and then you have ps. Ps is nothing but equal to cx omega from this triangle, from this square, and this is cx omega whole square. So from this identity you can get the amplitude of x. Take x common outside, you get f square is equal to x square k minus m omega square whole square plus c omega whole square. So from this identity you get x, take square root of both sides, you get x is equal to f divided by square root of k minus m omega square whole square plus c omega whole square. We will take only positive value while taking the square root, because we know that the displacement, the amplitude will be a positive quantity. Displacement can be positive, negative, but amplitude will be positive quantity. And now we have to determine phi is phi, the phase angle. So I have drawn the phi wrongly here. The displacement from the x-axis is the initial phase, but actually we have defined in our definition that phi is the phase angle between the force and the displacement. So since because f is equal to sine omega t, the forcing is equal to f sine omega t, and the displacement is capital X sine omega t plus phi. So phi is the phase between force and the forcing function and displacement. So in this diagram, the phi will be the angle between the vector f and the vector x. This also we can determine from this triangle OPS. So triangle OPS will give us tan phi equal to perpendicular by base. Perpendicular you can see here is equal to cx omega, and base again is kx minus mx square, mx omega square. So you will get cx omega in the perpendicular. In the base you will get kx minus mx omega square. X you can cancel out everywhere. You get tan phi equal to c omega by k minus m omega square. So you have our final solution as x is equal to this and phi is equal to this.